All right, good morning. So let's continue from the point we stopped yesterday. So just to remind you what we're doing. We're considering a flow between two plates, but now viscous fluid flows through the channel. And that means that the fluid gets stuck to the walls, so it cannot move through the walls, cannot move along the walls. So the velocity is completely equal to 0 at the walls. So, and we computed the base flow profile under assumptions that the flow is stationary, so steady, doesn't depend on time, and it is caused by a constant pressure gradient along the channel. And under the conditions that the plates are infinite, we cannot see the edges, so therefore we cannot see any distortions that could be brought in by the end effects, like entrance and exit from the channel. So we just assume that nothing changes along the direction of the flow, along the x direction. So we went through quite a lot of algebra, linearized the equations by introducing small perturbations and neglecting their higher powers. Squares of perturbations are neglected. We have obtained a system of equations that we then decomposed using a normal mode approach, or separation of variables, essentially. We assumed that perturbations can be represented as periodic waves written in complex form, complex exponential form. So complex exponential form assumes complex exponential behavior in x direction and also exponential behavior in time. We then went through a formal transformation, Square's transformation, and then we made a very important conclusion that if the flow is unstable in three-dimensional sense, so which means that waves propagate under some angle with respect to the direction of the main flow, then it is surely already unstable with respect to perturbations which propagate with the flow in the same direction. So there is no point for us to even spending our time on considering anything which deviates from the main direction. So therefore, our problem essentially becomes two-dimensional problem. And equations that describe the perturbations propagating with the main flow in the same direction along the channel, these ones. So we only have two velocity components and pressure. So we need three equations, and we have them. So we have two momentum equations, which become, after all these substitutions of exponential functions and cancellations, these ones, and the continuity or incompressibility condition, which becomes that. Okay. So, and I omitted all the Taylors and came back to the original notations of hat, simply to emphasize that we already proved that problem will have two-dimensional solution, and therefore what we have here is really physical. That's what we have. Tilde is was something we called equivalent, right, which is a result of algebraic manipulations, but now we prove that that equivalent tilde quantity is actually the real quantity, which we will see in experiments. That's why I do not need to use those tildes anymore. I come back to these notations, emphasizing that these are actually physical. So that's what we will see in reality. Okay, so what I will do next, and this is quite an important algebraic step, is that I will, instead of trying to write this in terms of stream function as we tried to do previously, we're not going to do that anymore. And this is pretty much thing of the past. So historically it is there, it allowed us to do a lot of things, but now we exhausted these benefits offered by stream functions, so therefore we will stick with so-called primitive variables. Primitive means original, u, w, and p. So I will therefore write them as a vector of unknown functions. Vector, which of course is a multi-component object, will be written like that. And I will call this vector in further notation just W with the arrow on top of that. That's not the same W. W hat is just a single component. W here is the vector which contains all three variables. Is that clear? So don't get confused. So the vector notation is quite important. Otherwise, you might get confused. But if it is a vector, then you know it is three components and only one of them is the actual W. Okay? All right. Now, what I will do next, I will write this system of equations in matrix vector form. How do I do that? So I know that vector is a table of values of coefficients of the equation. So I reserve a large space for that, and I will put the vector of unknowns on the right. U, oops. U hat, W hat, P hat. So what I would like to do is to write this system of equations in a matrix vector form. So vector will be multiplying this on the right. So, and the right-hand side will contain all of the right-hand side expressions or values. And right now, on the right-hand side, we have 0, 0, 0. So we have zeros, but 0 is repeated 3 times. So it is 0 vector. So I'll get 0, 0, 0, 3 times. Now let's go back to these equations and see what how the coefficients of the matrix could be found. So what you really need to do is to look for appropriate notation. So appropriate notation will be appropriate elements. So the first element in the vector is u. So let's identify all quantities which contain u. So you can see this one, and this one, and this one, 4 of them. Okay? So I will do one more thing. I will separate quantities multiplied by sigma from the rest of them. And to do that, I will introduce actually 2 matrices. So I'll just need a little bit of extra space. So I'll try to be compact. So, and I'll get another one here. So what do I mean by that? So first, I will factor sigma out and see that I have sigma in the first equation, and it is multiplied by u. Okay, so what we will have here is the sum of 2 matrices, right, in the brackets. The first matrix will be multiplied by sigma. So you can see that u appears on its own, except it is multiplied by sigma, right? So u is already factored outside, so therefore I simply put 1 here. So when I multiply sigma by 1, I will get sigma. When I will get sigma and multiplied by u, I will get sigma u. Is that clear? So it's quite trivial. So the same thing happens in the second equation, so in the second row, but now it will go, the second element will need to be multiplied, so therefore it will be here. There is no sigma in the last equation, in the continuity equation, and therefore the rest of the elements will have to be zeros. Okay, good. Now we will do the same thing with the rest of them. So we will see that the equations will contain u multiplied by I alpha u bar. I alpha u bar. They will be also multiplied, u will be also multiplied by alpha squared and divided by Reynolds number Reynolds number. So plus 1 over Reynolds number alpha squared And look at this. D squared, also, this is second derivative. But we will treat it as just an operator, which means we can treat it as a symbol. So essentially as a factor. So we will put minus d squared, but we will not put anything else next to it because we will assume that this whole thing is multiplied by u. Okay? So good. So I'm running out of space. I will probably need to erase that and shift everything to the right. Sorry for that. So make a lot bigger matrix. Okay. So is there anything else multiplied by u in the first equation? No, we don't see anything. So that's, yeah, no, that one is not there. So now we'll look for the next element, w. So where is w? So no w, no w, no w. So that's the only thing. So therefore, that is the element which we will need to add, du bar. Okay? Is there pressure? Here it is, I alpha. Do the same thing with the second row. So sigma w already taken care of. W, well, we're not looking for w, we're looking for u. We have to follow the order here. So no u, no u, no u. Is there anywhere, can you see u anywhere? No. So next one, w. So took care of that. And this will become I alpha u bar. So the same as before. Plus 1 over Reynolds number. Alpha squared, right? W goes outside, minus d squared. Is there pressure? Here it is. D. Finally, looking for u, I alpha. Looking for w, d. Looking for pressure, cannot find it. Okay? So that's what we have. So now let me call these matrices. So now I will not, I don't want to repeat writing them every time. So I will just introduce single symbol notations. And I call this matrix X, just capital X. And I will call this matrix Y, capital Y. So note that matrix Y contains parameters. It contains Reynolds number, contains alpha. Okay? So I'll put that like that. Alpha, semicolon, Reynolds number. Just to emphasize what it is. Okay? So it will contain those elements. So they are of different nature because Reynolds number is a physical parameter, right? It characterizes the flow from the very beginning, so from the experimental point of view. Alpha is a wave number, but it is our choice, right? So therefore, Reynolds number is whatever it is, whatever is dictated by the experimental conditions. Alpha is our choice, so therefore they have different nature. That's why I separated them. So it's not comma. They are of the same, of different nature, semicolon there. All right. So now my equation becomes sigma x plus y, the whole thing multiplied by vector w, is equal to 0 vector. So I will combine this into L of sigma alpha, semicolon Reynolds number, w is equal to 0 vector. So is that clear what I've done? So essentially L is sigma x plus y of alpha Reynolds number. Is that clear? So that's what that is. And I emphasize that L contains sigma, alpha, and Reynolds number. Again, sigma is something which we choose because, well, not choose, but it is dictated by alpha. We will see that, right? So when we choose alpha, then essentially we will get the corresponding sigma, and then we will get a Reynolds number, pretty much specified, frozen, fixed. We cannot change it. Okay, here we go. So now, where to from here? Well, this is a matrix multiplying a vector, and you will get 0. What's the obvious solution for this system of equations? So obviously, if W is chosen to be 0, then we will get 0. Multiply anything by 0, and you will get 0. Okay, so W is equal to 0, which means no perturbations. Clearly, this is of no interest. Right? So then we will need to make an effort to find the solution for W, which is non-zero. But essentially what we have, product here. So we know that the product is 0 if the individual factors, at least one of them, is 0. So W is not equal to 0. Full stop. Which means L has to be equal to 0. L is not equal to 0. So does it mean that we cannot have a solution? Well, it's sort of the first contradiction we encounter here. So, and the answer is, well, no, we still can have a solution. But what we mean by zero matrix has to change. It's not matrix, zero matrix actually, when you have zeros along instead of every single element. It's determinant of the matrix which needs to be equal to 0. So that's basic ideas from a linear algebra, but I would like to give you a little bit more information, or example rather, why this is so. Okay? So I will consider a very simple algebraic example, and bear with me, so some of you will find it trivial, but I still would like to go through that, because we will need that for much more subtle, to see a much more subtle thing happening later on. So I will start introducing this example here. So I will just consider a 2x2 system written in a form similar to what we just have here, 1, 0, 0, 0, plus, what did I choose? 1, 1, 2, minus 1, x, y, these are just variables x, y, and this is equal to 0, 0. So you see what I mean, right? So this is matrix X, this is matrix Y, but of course oversimplified. So to make sense of that, let's just obviously check here. If X is equal to 0 and Y is equal to 0, then no problem. Now, let me just rewrite this equation as a system of algebraic equations. And if I do that, I will simply get sigma from the first matrix, 1 from the second, so sigma plus 1, multiplied by x plus y is equal to 0. That's the first equation. Agree? So sigma 1, so sigma plus 1 multiplied by x, y multiplied by 1, y. Then nothing comes from here, from the sigma part of this equation, so therefore we will have 2x minus y is equal to 0. Agree? Well, immediately we see that y is equal to 2x, and then sigma plus 1 multiplied by x plus 2x, which is equal to sigma plus 3 multiplied by x is equal to 0. Agree? So clearly, if x is equal to 0, then this is 0. So the second equation is satisfied, but then y is equal to 0 as well. Agree? Okay. So, but this is of no interest. Much more interesting is this situation when sigma is equal to -3. If sigma is equal to -3, then this coefficient is 0. And x can be anything. And if x can be anything, then y can be determined to be just double of x. So therefore, in this case, therefore what we will do, we will just write sigma not equal to -3 means trivial solution. And sigma is equal to -3. In that case, we can say x anything. It still can be x equals 0, but it is still trivial. But importantly, that it is anything. So x is equal to a. Just to emphasize that this is some constant, not necessarily 0. Right? So therefore, y is equal to 2a. And in a vector sense, we will get x and y is a, 1, 2. Okay? We change a, and the vector just scales, becomes longer or shorter. Or maybe it flips. If we choose negative value of a, it will flip and it will point in the opposite direction. But overall, we will have infinitely many solutions. Okay? Well, it was quite clear that why sigma -3 is very special. Well, let me just go back and look at this equation. From a matrix point of view once again. So I glue these two together, and I will get sigma plus 1. So that's plus this. 1, 2, minus 1. So this is my matrix, and what will happen if I compute its determinant? So it is sigma plus 1 minus 2, which is equal to minus sigma minus 3. And if I set it equal to 0, I will get sigma equals to minus 3. Okay, we saw that sigma minus 3 does something special, and we now observe that sigma minus 3 makes determinant of the system of equations 0. So that's what it means. So it is determinant which is 0, which enables us to satisfy this equation. But in this case, we will get the solution that is parametric solution, which essentially says that we have infinitely many solutions. They all look the same, so all vectors are going to belong to the same line, but there will be infinitely many of them. So either trivial solution or infinitely many solutions. Okay? So this leads us to the idea, what we need to do here. So what we really need to do is to find the eigenvalues of this matrix. And one non-trivial thing is what is D. So alpha is a number, Reynolds number is an alpha, is a number, I is a number. So we can compute those as in pretty much standard matrix elements. But what about D? So even this is sort of, it is a derivative, but derivative consists of numbers, right? But what about this D? How do we treat that? So this is an operator, and this is, so real definition of that, so the actual definition of that depends on how you're going to solve this problem. And you're not going to solve this problem by hand. It's impossible. You will need to implement some sort of numerical procedure for solving that, numerical approximation. So D here will come from your definition of differentiation, numerical differentiation, whether it is finite differences, which are not recommended for this type of problems. I will tell you why a little bit later, or comes from spectral numerical methods. This is the method of choice for any stability problem. Okay? So that's what we need to keep in mind. That this is essentially a matrix on its own right, which is part of another matrix. Right? So this is a matrix which will somehow act on other elements in a vector and produce the result. So namely, what I mean by that. So for example, you have a function u hat, and this is u hat of z. You cannot solve this in a computer because it doesn't know what that z is. You have to say, well, I don't have z. You have z1, z2, z3, and so on. So you pick a grid of points, right? So you cannot really define the function. You have to define the function at particular points. So therefore you have u1, u2, u3, and these are the values of the function which you're looking for, but the values at specific points, grid points. Okay? So therefore, each of those components, u, w, and p, they become vectors on their own rights. They contain multiple components. Is that clear? So for example, if you have a grid with n points, then the vector u, v, w, and p will contain n elements for u, n elements for w, and n elements for p, 3n. If n is 50, the total length of the vector will be 150. Okay, which is quite a lot. And the matrix will be then 150 by 150. And we will need to solve find the eigenvalues of this matrix. So, and clearly, the number of eigenvalues, at least numerically, you will get 150 eigenvalues. Okay, so that's something to discuss. Now, what is D? Well, for example, if I want to use central differences, so in that case, how central differences work. So this is point 1, point 2, point 3, and so on. So you pick a point, for example, if you want to know what the derivative at this point is. So this is u1, this is u2, this is u3. And the distance between them is delta x. So therefore, u2 du2 is going to be u3 minus u1 divided by 2 delta x. It's just a simple example. This is not what is used in the actual procedures, numerical procedures. Some much more complicated spectral methods are used, but that's just to illustrate the example, illustrative example. So therefore, D is D times U, in this case, will be, so the second row, so because, well, I don't know how to define this one, I'll just leave it. So what we will put in this row here, the second row. So you see in this formula, we will have U1, so, and this is to multiply by U1, U2, UN. Right? So now you see that in order for me to define the derivative at the second point, I only need the first element and the third element from the vector. So therefore, I will put minus 1 over delta x here, over 2 delta x here. Then I don't need anything for this one. So you put 0, and then you put 1 over 2 delta x here. So therefore, and the rest are zeros. And this is going to create a band. So it will go like that. So at the next point, you will get exactly the same structure, but it will be shifted by one position to the right and so on. So you will get this band diagonal system. Okay? So that is what your D is. And that matrix will have to be inserted into the previous one. So that's just the idea of how it works. So what I will do next, I will actually show you what happens if I indeed solve this problem numerically, this particular problem numerically. I will run a MATLAB code, which I will put upload into the directory, into this folder, and you can play with it. So it uses spectral method, Chebyshev collocation method. So it is not my goal here to discuss that method here. I don't have time for that. So it is implemented there. You will be able to see that implementation. And if you are interested in that particular method, let me know, and I will send or just upload the references for from a published source, so published references there, right? So, but I will not be discussing that. So I'll take it as a black box. It works. It is tested and produces the right results. So this is the code. That's the name, Poiseuille or Poiseuille. Eval, so eval for eigenvalues. So what you will be able to see here, so I won't discuss it in much details. So, but the structure is, first I define service matrices for differentiation. So that's what I do here, and then I find the base flow. And the base flow, of course, is defined separately here at the end, which is very simple. Where am I? It's just a parabolic function. So let me see where it is. Not here, not here. Okay. Yes, so that's this function here. So it is base flow defined. We will need base flow and derivative of a base flow. Of course, in this case, I can define it analytically. So, and that's what I've done here. So this is a parabola. So, and then I form this matrix X, matrix Y. So they are called, I think in my notations here in the code, that is matrix A and matrix B. So matrix A is the one which contains alpha and Reynolds number. Matrix B is that is multiplied by sigma. That's what I do here. And I ask MATLAB to do the dirty job for me. So finding the eigenvalues. So therefore what I do here, I compute the eigenvalues using the command, standard MATLAB command eig. So if you're familiar with MATLAB, you should find it easier to follow. Okay, so and I find so essentially I ask the MATLAB to produce eigenvalues, and I'll just look at them. Remember that eigenvalues depend on alpha. And at this stage, I have no idea what alpha I should choose. From previous example, we know that alpha plays a significant role, because for some alpha, we might not have real eigenvalues at all, or we might have eigenvalues that have negative real part, which means they will not produce physical instability. So we are looking for eigenvalues that correspond to positive, that have positive real parts, and we need to identify the range of alpha for which it happens. So in the previous example, we could do it almost analytically by hand. Now we can't. So let's see what happens if I run this code for a range. So all I do, I just specify the range of alpha. So I will choose alpha range that is defined in line 24. Here it is just I pick randomly minimum value, maximum value, and say 100 values in between, or whatever number of them in between, and I run the code. And well, first of all, see how quick it is. Nowadays it's not a problem. So if I just press the button, and here we go. So it did it. And you can see if you can see, let me just modify the graphics a little bit. Let me try to run it again and see if it will help. Okay, so hopefully it is a little bit easier to see. So still not, well, can you see that roughly? Okay, so maybe you can see it on the screen over there if you're far away. So I compute them, and obviously I'm interested only in the ones which are close to 0 or above 0. So I choose my plotting range close to 0. You see that this is 0. The top one is 0. And lower edge is, well, I chose minus 0.2 here. So you can see that eigenvalues do exist. And this is just real part of eigenvalues, but they also have imaginary parts. So eigenvalues are complex, which means that the solution is oscillatory, right? It means that it not only grows, but it also oscillates. And these are the frequencies of oscillations, and these are growth rates. But the important thing is that remember, I have matrix 150 by 150, which means that numerically I have 150 eigenvalues. Not all of them are physical. Some of them will be just numerical artifacts, right? But the ones which are close to 0, the ones which are close to what we want, they are usually all physical. So what you, with the numerical methods, of course, you need to make sure that the convergence is achieved. So you have to have a sufficient number of discretization points, right? In this case, I think I chose 50. So you see that the eigenvalues form these lines. So even though I compute them at discrete points, well, it is easy to imagine that all these points are connected. Those are so-called model branches, eigenvalue branches, right? So that's what happens. And all of them essentially decrease, right? And they start, most of them start with negative values, and they decrease further. So therefore, we say that perturbation will decay. So it looks like the flow is stable. Now, let's try to recollect how it looks. It is a parabola. What can you say about the curvature of parabola?
So this particle is one minus the next way. What's the curvature of this? 5 net, well, that's area. So you give curvature to the second thing, and you differentiate parabola twice. What do we get? Of course, 1 minus z squared, right? If you differentiate with respect to z, what? You will get, of course, which is second the first step. What we know? Yes. Yes. Fine. Which one? Negative to right, so it's your question. So if it is 1 minus z squared, you can check what you will get minus 2. Minus 2 is a constant. Minus 2 does not change. Minus 2 is going to 0. What can we say about the parameter here? Well, it told us that for flow to be able to become stable, it has to have a reflection point. It does. Parabola doesn't have a reflection point. So, therefore, we come that this law, according to our has to stable. So that parabola should be visible, it should stay. Well, but Reynolds tells us so. Remember that experiment by Reynolds? So what's the contradiction here? All right. When you look at this picture, it looks like yes, everything is negative, but one of the mode of the lines, it is kind of the same shape. It goes down, and then it falls to the left. And I chose the value of Reynolds in the 66 window. I thought that it's actually easy. Reynolds already gave the 5772. It's 5772. And this is when this maximum touches zero.
And
If I choose the value of Reynolds number
but it's got to
larger than what I would hold it is, so you can see that's what I have, 5.7212. If I choose Reynolds number smaller than that, like 1,000 for example, I still be able to raise this picture and see it still has the maximum here, but it is well below the 0% still the upper range. So if I make it say 7,000 and run it,
but this is bringing this is the she's looking to no English but
then you can see that I'm already above zero. So zero, or you probably will be able to see that zero is slightly below the upper edge, and the highest point of this line at the edge, the upper edge, so it should be observing to be exactly like the top. And it is about zero, so it is already unstable. So, what
I'm into in the fundamentals. Yeah. So what I observe here, so the maximum sigma changes. It depends on Reynolds number. The larger the Reynolds number is, the larger the maximum is, the higher the maximum is. So therefore, we have a transition point, which is called the critical point. 5772, Reynolds number 5772 is a critical point at which at least one eigenvalue becomes positive, right? So at least at one value of alpha. That's what we have. And if we have Reynolds number higher than 5772, then the maximum will be above, but by continuity we will have a range of wave numbers for which eigenvalues will have real part, positive real part. So this is not a single point; it's the whole range of alphas which will give us positive growth rates. Okay, so that's what we need to remember. That's the conclusion. But back to the fundamental question: was Rayleigh wrong? Because we do have parabola, we know that it does not have inflection point. Rayleigh says it has to be there for instability. We see that instability is there. So what do you think happened? What's the resolution? Viscosity. We added viscosity. Rayleigh never considered viscosity. So viscosity plays a significant role. It creates instability. But if you think about it, it's actually somewhat counterintuitive. Why? Because when we consider viscosity, when we introduce viscosity, viscosity is friction. And what does friction do? It kills the motion, right? It kills the motion. So viscosity is there to take kinetic energy of the flow and convert it to heat. And if the fluid gets heated, that it stops. So conservation of energy principle. And here we will see that the viscosity actually is responsible for instability. Okay, it plays dual role. On one hand, it tries to stop the flow, so it makes it go to zero, so it makes it stable, right? So it tries to essentially annihilate the motion. On the other hand, it creates the motion. Additional motion. So perturbations are essentially additional motion which you add on top of the base flow, right? And this is, again, due to viscosity. All right. So that is something to keep in mind. So for this reason, the results for viscous flows, they cannot be extrapolated from inviscid flows. So there will be a qualitative transition. So viscous flows behave in a different way to inviscid flows. And that is something to keep in mind. So we can't really solve realistic problems without taking into account viscosity. It has to be there. And we cannot say in one word what will happen with viscosity, because viscosity can kill the motion, viscosity can induce the motion. Okay, so that's what happens. And how do I explain that? So in a very simplistic way, well, it's not quite rigorous, but I will give you an example. So remember, the perturbations, these are essentially some sort of structures which are stuck in the flow. And we have a shear flow. The flow, that means that layers of the fluid, they slide. And if you have interacting layers of fluid, now they interact, right? They interact with each other, so they feel each other. Inviscid fluid does not feel, it doesn't have interaction between layers, right? One layer slides over the top of the other and doesn't feel it. Friction, of course, introduces this interaction. So yes, I can feel both of my palms when I do that, right? So because there is friction, okay? And when I do that, I have to apply some force to overcome friction, right? I push my palm to do that. And if it is just purely mechanical system, so if I try to push this chair against the floor, right, quite hard, and if you need to move furniture, for example, office chair, how is it made? What's at the bottom? You will have wheels, right? Well, if you have these structures, they're like small wheels. That's what got stuck in the middle. And all of a sudden, you see what happens? Instead of just dragging one layer over another, you're actually rolling it over. So, and this is the reason why instability is produced. So that's actually helped in a sense. But of course, you need to do that, you need to make this thing spin. And that spinning motion requires energy. So you lose some energy to start that spinning process, but you gain advantage because the friction, or after that, the friction is reduced. Okay, so that is what happens physically in these systems, and that's why the answer to the question is far from trivial. So you cannot say for sure what dominates. So clearly, to make this thing spin, you need to input at least some sort of minimal energy. So therefore, Reynolds number has to be sufficiently high so that the base flow can provide that energy, right? If the flow itself, the base flow, is weak enough, it will not be able to lose much energy without dying itself, so that to create even initial motion, right? So it has to be of appropriate strength to do that. And once you overcome this limit, then it actually helps you, right? That's how it works. So, but you need that threshold energy to start the process. Okay, now let us just see what else we can extract from numerical simulation. So I'll come back to the case of critical Reynolds number, just for definiteness. So it is 5772. And run it again. So that's what we see, one of the pictures. So we discussed that, and you can see that the imaginary part is not equal to 0. That means that we do have oscillations, and what we have, oscillations in space, because we have alpha, non-zero alpha, right? So we have non-zero alpha, so you have a sort of wavy structure in space, and you have oscillations, temporal oscillations. So therefore, what you have is combination of two oscillations, spatial oscillation and temporal oscillations. That's a wave. So, and I will show you how it looks in a second. So it is a wave which propagates through the channel. or along the channel, because we know it propagates in the same direction as base flow. So it is a wave which is on top of the base flow. And this wave was first discovered by this type of analysis in 1930s, and it has a name attached to that. It's Tolman-Schlichting wave. And these are so-called boundary layer waves. They occur in boundary layers close to the walls, okay? And they are a prominent feature of any channel flows, like parallel base flow, but also any boundary layer. So boundary layer, for example, on the airplane. So airplane flies through the air, right? And the air goes along the wing, the surface of the wing, so it cannot slide on exactly at the surface of the wing, so therefore it gets stuck to the surface of the wing. But away from the wing, of course, it doesn't know about the existence of the wing, it stays where it is. So therefore you have this velocity profile, non-trivial velocity profile, which is called boundary layer profile. So something, velocity changes quickly in the close proximity of the solid surface, like airplane wing, but outside of this boundary layer, away from it, just nothing happens. Right? When airplane flies in 10 kilometers in the air, you do not feel anything here. So, okay. This is my Poiseuille flow. So this is parabola. And what I can do is to determine the quantity which is called wave speed. Remember that parameter C, which I introduced formally. Okay, so I'll just go back for a second. Okay. It was a few slides back. So I already have C here, right? So C is I sigma R divided by alpha minus sigma I divided by alpha. Agree? So sigma contains real and imaginary parts, so if I take imaginary part, multiply, so it has I in it, multiply by another I, you will get minus, but this combination here will be real, so that's real part, right, of this combination. So this is wave speed. Okay? Is that clear why we call it wave speed, or should I show it to you? So do you know how waves are described? Okay. So if you are not quite clear about that, just ask me after the lecture. It's literally 1 minute explanation, but I would don't want to get distracted now. So this quantity is a wave speed, and I will show you. If you don't know why it is called wave speed, I will show you very quickly, but after the class. So, all right. Bottom line is that I know my sigma. I computed my sigma, both real and imaginary part. I know my alpha because I chose it. So therefore, I can determine this ratio, sigma I over alpha. And then I look for a point in the flow where this wave speed is equal to the local velocity. Okay, that's what I'm doing. And this is what I get. So again, you might or might not be able to see it from the distance. So this is my parabola. That's the base flow. And these two horizontal lines, which are close to the walls, they represent the location, Z location, where the local velocity of the base flow, so this point on this on the blue line, is equal to the computed wave speed. Okay? So that's the location where the wave speed is exactly equal to the velocity of the base flow. Why do you think I'm looking for that? So what do you think might happen there? So if two objects, one is the wave, the other one is base flow, a fluid particle, they move together there, right? So they do not, there is no lag between the two. They come together. And that means if they come together, they have a lot of time to talk to each other, right? If I'm going through the class very quickly and I'm you're just sitting there, right? I cannot talk to you. I have to stop next to you to talk to you, right? So we need to be moving with the same speed. If we're driving in the car, in different cars, we cannot talk. If we're driving in the next to each other, open the window, you can talk to each other and abuse each other, right? So that's what you know. So that's what just common sense. So therefore, this means that at this location, there is a good chance for you to exchange things. And what I mean here by exchange is, well, most of all, I'm concerned about energy exchange, because perturbations have to feed themselves. They need to take the energy from somewhere. Where can they take that energy? Well, the only way they can take the only source of energy they might have is from their parents, and their parents is a base flow, right? So let me just look at the so-called eigenfunction. So remember, I compute eigenvalues, but I also have eigenfunctions, which are those hat quantities, u bar, u hat, w hat, and p hat. So I can actually compute, well, MATLAB can do it for me. So I don't worry about that. MATLAB does it for me. So what I want to do is just plot it and see what happens. And that's what happens. This is the measure of exchange, energy exchange between the base flow and perturbations. So how it is computed, it is explained in my notes, handwritten notes. And I probably would like to skip the discussion of that, because there is a lot of algebra there. But the bottom line is, it is possible to say, to determine the energy exchange rate between base flow and the perturbations, and you can do it algebraically. The expressions are quite lengthy. You have to spend a bit of time integrating things, and so probably if I were to explain that in detail, it would probably take me an hour or so. So I'd rather not do that, but it is in my lecture notes, handwritten notes. You will be able to read it if you are interested in that. So the bottom line is, if I compute that energy exchange rate, that's how it looks. So the exchange happens everywhere, and that exchange is not necessarily always positive, because, well, the zero level is here. That's zero. You can see that there are places where the energy goes back to the flow, to the base flow. So essentially, the perturbations pay back some money or whatever, some energy back. But by far, they take more. Well, it's sort of like children, right? So you support, as a parent, you support them, and they give you a birthday present once a year. So they pay back to you a little bit. So, all right, here we go. So this is all physically meaningful. And this is just a formal solution. So obviously, computers doesn't know what it is doing, right? So it just produces the numbers and you plot them. But the interpretation is quite straightforward. So eigenfunctions, or the solutions, are such to ensure that exchange happens in the most efficient way. And that commonly happens when you have communication time. Sufficient communication time, and for that you need to move with the same speed. So therefore, this layer here where exchange happens, it has a name also. It is also called critical layer. So perturbations are born and raised at critical layers, where exchange between parent flow and perturbation children, disturbed children, happens. Right? So that's what happens. That's what the physics of that is. Very straightforward physics behind mathematics. Mathematically, you do stuff, but really, the important thing is how you view that, how you interpret that. That's what happens. Let me see if I have anything else to show you. Okay. 5 minutes. Yeah, I'm about to finish. And, okay, so this is the full field. If I compute my perturbations, right, I have U component, I have a W component. U component is in this direction. W component is vertical direction. Pressure is obviously a scalar. And they just plot them, so I have two-dimensional plots. So these are the velocity fields created using my solutions. You can see how they look. So obviously I assumed periodicity in space, and you can see these cells. So that's how they look. They are looking like rolls. Okay? But remember, these rolls do not exist on their own. They are on top of the base flow, which is a parabola. And these rolls, remember also the main assumption that we made the amplitude of these, we assume that the amplitude of these rolls is small, so that we can neglect all the nonlinear effects squares, right? So therefore, this is what we see on it if we plot them on their own. But that's what will happen if we try to overlap them. Hardly can see anything here, right? So that's just your parabola. Okay, so therefore, that's what we need to keep in mind. These are there, but they are small, relatively small. So when you add them to the base flow, you might not even be able to see them, right? But we clearly can separate them mathematically. Experimentally, you cannot do that. That's what you see experimentally. So you look hard and you cannot see anything because your experimental resolution is not good enough. The camera is not good enough. Your eyes are not good enough, whatever. But mathematically, you can do that. So, okay. So that's this thing. And and then I made them move. Okay. So I think just hopefully you saw some motion. I don't want to run it again because we're running out of time. So did you see them? So they actually move. And if you come close, maybe during the break you come close and I run it for you, and you just come close and you see it for yourself, right? So you will see that base flow, if it is set in motion, you will see those waves propagating in the boundary layers. Okay? So what I suggest, we probably stop now, and you guys come close. I will run it at the close range for you. So and then after the break we will continue.